In Chapter 5, we switch gears a little bit and talk about one of the important foundational parts of statistics, which is probability. This chapter is probably going to have the most material that you might remember from other classes. So hopefully some of this will be a review, but some of it will also be new stuff as well. In fact, in statistics, we interpret probability completely different than we do in any other course before now. It's almost like relearning a definition. And in fact, for us, probability, proportions, and percents are all the same thing. There is no difference. So when we find that something happens a certain proportion of the time, that means that it has a probability of happening that proportion of the time. Okay, so here's how we interpret a probability. Okay, probability is always going to be a number between 1 and 0. And we represent probability by saying the probability of X. Okay, it's always going to be a number between 1 and 0. And what it is it's the proportion of times the outcome would occur in a very long series of repetitions. So if I repeated something over and over and over again, what proportion of times would a given outcome occur? That's probability. Okay, we also think of it in terms of, we call it long range relative frequency. Relative frequency basically means proportion. Long range means over a long period of time. Okay. It's important to know that there are two types of probability that we talk about in classes before this. You've probably talked about theoretical probability, so what should happen, and experimental probability, which is what actually does happen. So in theoretical probability, I say that if I flip a coin, the probability that I'm going to get heads is 1/2, because out of two sides there was one heads. Experimental would be if I flip that coin 10 times, exactly what proportion of times did I get heads. So it may not be 1/2. However, we have this law of large numbers here that tells us that the more often something is done, so the longer the series of repetitions, the more likely the theoretical probability and the experimental probability will equal one another. So the more times that I do an event, the more likely the theoretical and experimental probabilities match. So if I flip a coin 10,000 times versus if I flip it 10 times, I'm more likely to flip heads about half of those times. Okay, so let's look at a problem that involves probability. So how much should a company charge for an extended warranty for a specific type of cell phone? Suppose that 5% of these cell phones are under warranty will be returned, and the cost to replace each phone is $150. If the company knew which phones would go bad, it could charge $150 for those phones and $0 for the rest. However, the company won't know. They just know 1 in about every 20 will be returned, so how much should they charge for their extended warranty? So basically, when you purchase an extended warranty on something, whether it be a phone or I have one on my refrigerator, what you're paying for is you're paying enough money to cover the likelihood that 1 in every 20 of these is going to be returned. So basically, they're splitting the cost of 1 among 20 people in order to cover the costs. So, because they know that about 1 in every 20 will be returned, they can say, okay, well, then that means out of every 20 phones, I need to make $150. So, I take $150, I divide it by 20, and that tells me that each person should pay about $7.50. Okay, will that always be that 1 in every 20 will be returned? No, I mean, they may have 2 and then they may go 60 phones and none of them be returned. That's the thing with probability, is that you don't know which one is going to happen from one thing to the next. I just know over a long period of time. So if I sell millions and millions of phones over that long time, about 1 out of every 20 is going to be returned. So I can estimate how much I should charge for my extended warranty based on that probability. Okay, so let's check our understanding from page 286 about just the foundations of probability. The foundations of probability. So 1, according to the Book of Odds, the probability that a randomly selected U.S. adult usually eats breakfast is 0.61. So we would write that like the probability that someone eats breakfast, 0.61. Okay, explain what the probability 0.61 means in this setting. That means that if you asked a large sample, okay, a lot of people, a lot of repetitions, if you asked a large sample of U.S. adults whether they usually eat breakfast, about 61% of them will answer yes. Okay, I have all the keys to my probability definition here. I'm saying that I took a large sample, so there's a lot of them. I talk about my who I'm sampling, what the probability is about, and there is my probability right there. Okay, it's important to notice that I did not give a number to how large of a sample I took. It's not that I can say out of 100 people, 61 are going to say yes, because I don't know that. There's no way for me to know who's going to say yes and who doesn't before I ask. However, I know, thanks to the law of large numbers, that if I ask a large enough sample, about 61% of them will say yes, because 61% of the population eats breakfast. Okay, so problem 2 says the probability is a measure of how likely an outcome is to occur. Match one of the probabilities that follow with each statement. Okay, so A says it's impossible. Probabilities that are impossible have a value of 0. Okay, probabilities that are impossible have a value of 0. If it is impossible that it will occur, it is 0. B says the outcome is certain. It will occur on every trial. Okay, that's on the flip side. If something is certain, it has a probability of 1. This outcome is very unlikely, but it will occur once in a while in a long sequence of trials. Okay, if it will occur once in a while in a long sequence of trials, something very unlikely, that's probably this 0.01, because that means it's going to occur at about 1% of trials. And D, this outcome will occur more often than not. Okay, well, we know it can't be 0.3 because that means that it only occurs 30% of the time. So that leaves us with 0.6 and 0.99. Since they're saying it's going to occur more often than not, that means it's going to occur more often than 50%, but probably not so close to 1 that it would occur almost all of the time. So it's probably going to be 0.6. Okay, in addition to probability, something that goes right along with that is the idea of randomness. Okay, there are 2 myths about randomness. Our 2 myths are, 1, that probability is predictable in a short run setting. That is a myth. Okay? Even if I flip a coin 5 times in a row and I get heads every time, that does not mean that I am due for tails. Okay? From one time to the next, probability is not predictable. All I know is that if I'm flipping a coin, if I do it a bunch of times, I'm going to end up with about half heads and about half tails. Not exactly probably, but somewhere about. Okay? I cannot do any kind of predicting from one term to the next. Okay? The other myth about randomness and probability, okay, is the law of averages. Okay, the law of averages says that everything has to even out in the end. So there is a great example about a couple, and this example is in the book, is that an advice columnist published a letter from a distraught mother of 8 girls. It seemed that she and her husband had planned to limit their family to 4 children, but when all 4 of them were girls, they tried again and again and again. After 7 straight girls, the doctor assured her that the law of averages was in their favor 100 to 1. Okay? However, there is no law of averages. Just because it's a 50-50 chance doesn't mean that after I've had 7 girls, I'm gonna still have another girl. I'm gonna have a boy. The chance is just as likely to have another girl as it is to have a boy, because probability is the same in short term. Like, it doesn't matter what has happened, my chances are still the same. And actually, this couple had another girl. So do not be fooled by the law of averages. So let's look at a couple of examples. If you roll a die 12 times and record the result of each roll, which of the following outcomes is more likely? Notice that this is 1, 2, 3, 4, 5, 6, 6, 5, 4, 3, 2, 1. And this one, they all seem pretty random. There is no pattern like there is here. We want to say that this one is more likely, because to us, probability means a sort of randomness, that there should not seem to be any pattern. However, from one roll to the next, okay, short term, from one roll to the next, it's just as likely to get this 2 as you are to get this 5. And you're just as likely to get this 3 as you are to get this 4, because on a die, there's a 1 in 6 chance of rolling any number, and the probability for all the numbers is the same. So here, each of these has the exact same probability of occurring as the other one. Okay. In casinos, there is often a large display next to every roulette table showing the outcomes of the last several spins of the wheel. Okay, does this help players? Again, we want to look and think that this plays into the law of averages. If red has happened a bunch, then I may think, oh, well, I'm going to bet on black because black is due. Okay, there is no such thing as something being due when it comes to probability. Red has just as much chance as occurring as black does. So this actually doesn't help players. Often it probably hinders them because they get into their head thinking about the law of averages, when in this case the law of averages doesn't exist. Okay, this is probably even a play by casinos to help people want to play, to say, oh, there's a bunch of streaks of red, black is due. Let me go ahead and bet my money on black. When in truth, nothing like that helps at all. So some important things to remember about probability. Long-term relative frequency. With probability, it doesn't help us at all from one thing to the next, from one roll of the die to the next, or one spin of the roulette wheel to the next. Probability doesn't help us at all. Not unless there's some case where something is 2 times more likely or 3 times more likely to happen. However, what we're looking for in terms of probability is what's going to happen over the long run. How does this help me if I plan to do this over and over and over and over and over again? And remember that randomness just doesn't mean that it looks random. This is as completely random as this is.